Hi everybody, I hope this video finds you well. In today's video, we're going to be working on section 4.8 from your textbook, which introduces you guys to a couple of interesting sort of vector spaces that can be generated by looking at the rows and columns of a matrix. So in this video, what we're going to do is we're going to look at a couple definitions, make a couple comments, and then look at a few examples trying to illustrate these ideas. Just sort of like section 4.7, we're going to do this section relatively quickly because while it is interesting and it certainly gives us some more sort of unique spaces that are generated by a structure that we've studied a lot, which are matrices, it doesn't necessarily fit the direct flow of where we're headed, trying to basically use our new knowledge of vector spaces to help us get back to understanding how to solve higher order differential equations. So we'll put some definitions here and we'll do some examples, but we're not going to necessarily be as detail oriented in this section as some of the earlier ones. So let's go ahead and start in with our definition here. So let's let A be an m by n matrix. Then we're going to define two spaces here. The row space of A is the span of all the rows of A and is therefore a subspace of Rn. Now, for a moment there, let's make sure we understand why it's a subspace of Rn, right? If we're letting A be an m by n matrix, well, then each row, right? If you think about it, each row will have n elements in it, right? Because there are n columns. So each row will have n elements. So each row will be an element in Rn. Therefore, when you take the span of all those rows, remember the span of any set of vectors is automatically a subspace. So we know that this row space, which is the span of all the rows, is a subspace of Rn. Similarly, the column space of a matrix is the span of all the columns of that matrix and is therefore a subspace of Rm because, again, each column will have m elements because there are m rows, so the span of the columns will live inside of Rm. And we denote this guy col space of A. Okay, so we've defined these two new spaces, and from our knowledge way back, like when we first talked about span, so section 4.4, we know that if you take a set of vectors and you talk about the span of that set of vectors, it is automatically a subspace. So we know that these two things are new subspaces. Now, more recently, our interest is always making sure that we know how to find a basis for a given subspace. Finding a basis for a given subspace is important, remember, for two reasons. One, it tells you how to build everything in that subspace, and two, it tells you the size or dimension of that subspace. So let's talk about how you would find a basis for each of these two spaces. So a basis for the row space is very easy. It can be found by simply using the non-zero rows of the row echelon form of A. Now, in your textbook, there's a somewhat lengthy derivation of exactly why this is the case. Again, because this is a little bit tangential to our overall flow of the course, we're just going to give that as a sort of verbal explanation. The reason that this should sort of make sense here is that when you put something into row echelon form, what you're doing is you're doing different elementary row operations. And as you guys know, there's three major elementary row operations. There's interchanging two rows, there's multiplying a row by a scalar, and there's adding a multiple of one row to another row. If you think about what each of those are doing, though, interchanging two rows, well, that's obviously not going to change the span. Multiplying one by a constant multiple, that's not going to change the span because, as we know, a constant multiple of a vector is linearly dependent, so that's not going to change the span. And finally, adding a multiple of a row to another row, well, that's building a linear combination out of the rows. So if you build a linear combination out of the rows, that's not going to affect the span because that's linear dependence. So, in other words, all those elementary row operations, they won't affect the span. So you can do all of those as you wish, put something into row echelon form, and then, of course, only the non-zero rows are contributing meaningfully to the span. So when you talk about the row space, the easy way to find the basis for it is by simply putting it into row echelon form and grabbing all of those non-zero rows. Now, the column space is a little bit trickier. The reason that the column space is trickier is that the column space is about the span of the columns. So doing elementary row operations, well, as their name would imply, are elementary row operations. However, there's still a pretty clever trick here. The way you can find the basis for the column space is by using the original columns of A that correspond to the pivot positions of the row echelon form. So in other words, while the row echelon form actually changes the span of the columns, it identifies which of the columns are contributing meaningfully. So, as we'll see when we do our examples, the way to find a basis for both the column space and row space is to put the matrix into row echelon form. For row space, we will literally just take the non-zero rows of the row echelon form. But for column space, we'll instead identify what the pivot positions are and then use the columns of the original matrix. Now, in both these situations, interestingly enough, because the number of pivot positions is equal to the number of non-zero rows when you put something in row echelon form, it shouldn't be hard to believe that the dimension of the row space will be the dimension of the column space, which will be something that we've actually already discussed, the rank of the matrix. Now, this is a really interesting statement here because this is saying that the dimension of the row space and the dimension of the column space is going to always be the same. This does not mean, though, that the row space and the column space are the same. In fact, it doesn't even make sense a lot of the time to talk about the row space and the column space being similar because they actually live inside of different vector spaces, right? The row space is always inside Rn, and the column space is always inside Rm. But their dimension is always going to be equivalent. That's the importance of this note here. Okay, so with these definitions and with this stuff in mind, again, we didn't prove that these two things will always work, but your book does go through a derivation of that. Instead, we'll jump into some examples of doing this, being able to generate a basis for the row space and column space. So let's get into looking at those. All right, so here's our first example. We've got this matrix A here. We're going to determine a basis for the row space, for the column space, and we're going to stretch way back quite a few sections ago. I think back in like section 4.3 or something, where we talked about the null space. Remember, the null space are all the sort of vectors that are solutions to the homogeneous set of equations with these coefficients. So we're going to determine a basis for these three special spaces determined by this matrix A, and then we're going to state the dimensions of all three of these spaces. Okay, so let's start by trying to find a basis for the row space of A. So what we're going to do is we're going to start with our matrix 1, 2, 1, negative 8, 1, 0, 0, 3, 12, 0, 2, 4, 5, negative 4, 0. So we've got to put this into row echelon form. So let's go ahead and start by taking R3 and replacing R3 with R3 minus 2R1. So we get 1, 2, 1, negative 8, 1, 0, 0, 3, 12, 0. And then when we subtract here, it looks like we get 0, 0, 3, minus 4, plus 16. So I guess that's 12. And then 0, minus 2 there, right? So we get minus 2. Okay, so there we go. We get this guy right here. Okay, so this gives us our first operation there. I believe that all looks good. Let's just make sure. R3 minus 2R1. I don't know why I'm hesitating, but no, I'm just going to make sure. Yep, 2 minus 2 there. Yep, that's 0. 2, 4 minus 4. Yep, 5 minus 2. That's 3. Negative 4 plus 16. That is 12. And 0 minus 2. Yep, okay, all looks good. Alrighty, let's go ahead then and continue on. Now we can use this guy to remove the stuff down below. So we can take R3 and replace it with R3 minus R2. So when we do that, looks like we should get 1, 2, 1, negative 8, 1, and then 0, 0, 3, 12, 0, and then 0, 0, 0, 0, and then minus 2, minus 0, so minus 2. All right, last thing, I guess, is if we really just want to clean it up into row echelon form, we can divide by 3, divide by negative 2. So 1/3 row 2 and negative 1/2 R3. So it looks like we should get 1, 2, 1, negative 8, 1, 0, 0, 1, 4, 0, and 0, 0, 0, 0, 1. All right, now that right there is our row echelon form of this thing. Okay, so let's use this then to determine a basis for the row space. So if we look at this, the basis for the row space would be these three vectors. So for A, the basis for row space of A would be, well, it would be vector 1, 2, 1, negative 8, 1. Also 0, I guess I can put commas there, right? 0, 0, 1, 4, 0, and 0, 0, 0, 1. Okay. So there we go. There's the basis for the row space of A. It's just the non-zero rows of the row echelon form. Okay, we can also use this to quickly get a basis for the column space. We can see that the important sort of pivot columns are column 1, column 3, and column 5. So the basis then for the column space of A will be these 3 columns there. So we can go ahead and do that as well. Basis for column space of A is going to be equal to 1, 0, 2. And so we're using this guy, and this guy, 1, 3, 5. 5. And finally the last guy, which is 1, 0, 0. Okay, now, interestingly enough, right, again, as you guys should notice here, right, the dimension of the row space and the dimension of the column space is going to be the same. We've got 3 vectors in each. Obviously, they're very different, though. These 3 vectors in here live in R5, whereas these 3 vectors in here, right, actually live in R3. In fact, we actually now know that the column space of A is actually equal to R3. And the reason we know that is because the basis for the column space is 3-dimensional, and R3 is 3-dimensional. And remember, we said that if the dimension of a subspace is ever the same as the dimension of the vector space, then those spaces are actually equal. So as a note, as a little follow-up here, we've actually just learned that as a space, the column space of A is equal to R3. Does that mean that the row space is equal to R3? Well, it doesn't even make sense to say the phrase row space of A equals R3 because the things in the row space live in R5. But it makes sense to say that about the column space. Okay, now let's go ahead and get that null space. So as just a quick reminder, recall null space of A. Remember that right there is the set of vectors x such that ax equals 0, with x an element also of Rn. Why does x have to be an element of Rn? Well, because A is m by n, right? And then if you're multiplying by a vector, right, it would have to be n by 1 to make the matrix multiplication make sense, so that x is in Rn here. So, do we need to re-solve this? Well, no, we can actually use the row echelon form, because remember, if we had been doing the null space, what we would have been doing was augmenting this with 0, 0, 0 along the way. But every time you do one of these operations, the augmented part, because it's all zeros, is just going to remain as all zeros. So you can actually just jump right to here, augment that with zeros, and look at the solution set. So we can jump right to this guy here. 1, 2, 1, negative 8, 1, 0, 0, 1, 4, 0, and 0, 0, 0, 0, 1. Augment that with 0, 0, 0. Well, what does this tell us? Well, we're going to avoid parameterizing these guys, right? Let's do this sort of in red. Red is a good avoidance color. All right, so we're going to avoid these guys. So let's go ahead and let's let, I guess we call it x4 be equal to t and x2 be equal to s. So what do these equations tell us? Well, it tells us that x5 needs to be 0. It also tells us that x3 plus 4x4 plus 0x5 must be 0. So that tells us that x3 plus 4t is equal to 0, and x3 is negative 4t. Finally, if we go to this equation here, that tells us that x1 plus 2x2 plus x3 minus 8x4 plus 1 plus x5 has to be 0. That looks horrendous, so let's just give ourselves a little bit more room there. Okay. So that tells us, the last equation tells us x1 plus 2x2 plus x3 minus 8x4 plus x5 has to be 0. So that tells us x1 plus 2s minus 4t minus 8t plus 0 needs to be 0. And that looks like x1 is 12t minus 2s. Okay, so what does that tell us there? Well, that tells us that the null space of A are all the sort of things that look like 12t minus 2s, s, negative 4t, t, and 0. Okay? Now, does that give us a basis? Well, no, but it gives us a general element. So choose one of the parameters to be 1, the other parameter be 0. And this tells us that a basis here would be, well, let's let t be 1 and s be 0. So it looks like that guy would be 12, 0, negative 4, 1, 0. And then if we let s be 1 and t be 0, that looks like we should get negative 2, 1, 0, 0, 0. So there we go. So there's our basis for the null space. Notice that we did the null space a little bit differently. We figured out what the overall null space looks like, and then we realized that since we had the general element, we were able to get the basis just by simply letting this guy was t equals 1, s equals 0, and this guy was t equals 0, s equals 1. Okay, last thing we sort of wanted to note here was the dimensions of all these spaces. Sort of running out of room a little bit, but I'll just try to squeeze in so we don't do weirdly another sort of sheet, right? The dimensions here, dimension of the row space was equal to 3. The dimension of the column space was also equal to 3. And the dimension of the null space was equal to 2 here because we had 2 basis elements. Okay, so there we go. We went through, we found a basis for the row space, a basis for the column space, a basis for the null space, and discussed their dimensions, right? Remember, these two, dimension of row space and column space, will always be equivalent, and the dimension of the null space, as we'll actually investigate in the next section, has a direct relationship with those as well. All right, let's take a look at one more example of this. All right, so we've got another matrix here, right? Matrix A, it looks like it's a 1, 2, 3, 4, 5, 6. It's a 6 by 3 matrix here. We're going to do the same thing. We'd like to figure out something for the row space, column space, null space, and then state the dimensions. Okay, so let's start with A, the row space. So what we need to do is figure out how to put this thing in row echelon form. So let's take our matrix here, 1, 3, minus 1. 3, 9, minus 3, 1, 3, 0, 1, 3, 3, 5, 15, 1, and 2, 6, negative 1. Okay, so let's start by just using this guy to wipe out everything below it. So I guess we're going to have to replace R2 with R2 minus 3R1, R3 with R3 minus R1, R4 with R4 minus R1, R5 with R5 minus 5R1, and R6 with R6 minus 2R1. So we do all that, and we get 1, 3, minus 1. Then it looks like we're going to get 0, 0, and 0. Okay. Then looks like we're going to get 0, 0, and what is that? 0 minus 1, so 1. And then looks like we're going to get 0, 0, and what is that? 3 minus negative 1, so 4. And then it looks like we're going to get 0, 0, 1 minus plus 5, so 6. And then finally we're going to get 0, 0, and then minus 1 plus 2, so a 1 there as well. Okay, so probably a good idea then, maybe to put one of these 0, 0, 1s up there, and then also use whichever one we put up there to zero out everything below it. So let's go ahead and sort of do that. I guess we can interchange R2 and R6 real quick. 1, 3, minus 1, 0, 0, 1, 0, 0, 1, 0, 0, 4, 0, 0, 6, and 0, 0, 0. Okay. Now we can do R3 and replace it with R3 minus R2, R4 and replace it with R4 minus 4R2, and R5 and replace it with R5 minus 6R2. So we should get 1, 3 minus 1, 0, 0, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, and of course we already had 0, 0, 0 at the bottom. So there we go, there's our row echelon form. So we grab the non-zero rows here, 1, 3, minus 1, and 0, 0, 1, and those will be our basis for our row space. So basis for our row space is going to be the vectors 1, 3, minus 1, comma, 0, 0, 1. Okay, there we go. So that's our basis for the row space. Can we also use this to get our column space? Yep, well, same idea. Remember, we just grab those pivot positions. So it's the first and third columns. So we will use the first and third columns from the original. So we can say for B, basis for the column space. Again, we don't use these guys because these have been modified according to row operations, not column operations, but they tell us which columns we want. We want that first one, which was 1, 3, 1, 1, 5, 2. And we want the third one, which was -1, -3, 0, 3, 1, minus 1. I also hope you guys can see why we don't want this second column in terms of the column space. You guys should be able to very clearly see that this second column is just 3 times this first column, and we know that something that is a scalar multiple is automatically linearly dependent and is not contributing anything to the span. So this guy is useless in terms of contributing to the span of the columns. So our basis for our column space is right there. Notice again, rank of this matrix is 2, and that's the dimension of the row space and the dimension of the column space. Let's go ahead and do the null space on the next page. We'll just grab our matrix here, because remember, we can just use this form here. So let's give ourselves one more page to do this. So we want to do our null space. Okay. Let's go ahead. Paste that guy here. Okay. Now let's just go ahead and modify that. We actually want to augment it. 0, 0, 0, 0, 0, 0. Okay, we can solve that. Remember, this time we want to, I'm just going to erase these guys here so we can do it in a slightly different color. Right. So do keep in mind here, we want to avoid parameterizing these guys. So what we would do is we'd let x2 be equal to, say, t. Then we would learn that x3 needs to be 0, and we'd learn that x1 plus 3x2 minus x3 needs to be 0, which would tell us x1 plus 3t needs to be 0, and x1 needs to be negative 3t. So this would tell us that the null space of A would be all the vectors that would sort of look like negative 3t, t0. Okay? And then, of course, to actually figure out a basis, well, there's only one parameter. So the basis here would just be consisting of a single vector. We could call it -3, 1, 0. Okay. Now, that would tell us then, in terms of dimensions, right, that the dimension of the row space equaled the dimension of the column space equaled 2, and the dimension of the null space in this case was equal to 1. Okay, so that gives you guys a couple examples of looking at row space, column space, and null space. Now, before we call it good here, I do want to just make one mention about the relationships between these dimensions. Obviously, these guys are not guaranteed to be equal, right? We just saw in 2 examples where they got different dimensions. But let's notice that there is a relationship here. So let's look back at the first one. In the first one here, we got these guys to be 3 and this to be 2. Let's think real quick. What's the sum of this? Well, these guys are 3 and this is 2, so the sum of that would be 5. Well, does 5 show up anywhere in here? Well, 5 does. It's the number of variables or the number of columns, right? This had 5 columns in it. And it's not a coincidence that these two, the rank, which is the dimension of either of these, and the dimension of the null space sum together to be 5. Let's see if that's true in the other one. Here, there are 1, 2, 3 columns. And if we check, the dimension of the row space and column space was 2, plus that 1 for the dimension of the null space is 3. In the next section, 4.9, we will prove that. It's what's called the rank nullity theorem, and we'll see how that relates to understanding solution sets of homogeneous equations to solution sets of non-homogeneous equations, which is a very important concept as we move closer back to returning to differential equations.